Hello dear student, welcome to another lecture in Dynamics of Rigid Bodies. This is the last lecture, lecture number 6 in Dynamics of Rigid Bodies. So far we have learned about moment of inertia, theorems of moment of inertia of different rigid bodies, and also about kinetic energy of rotating bodies. In this video, we will learn about flywheel. This is an application of moment of inertia. So we will learn about flywheel, what a flywheel is. Then we will look into how to find the moment of inertia of a flywheel using experiment. We will look into its theory and the experimental analysis. Then to the end, we will look into the applications of flywheel in our daily lives. So, what is a flywheel? A flywheel is a mechanical device specifically designed to use the conservation of angular momentum so as to efficiently store the rotational kinetic energy. We know that when a body is rotated, it will have an angular momentum. Angular momentum is a rotational analog of linear momentum. We have learned about angular momentum in our previous video. Angular momentum is a conserved quantity. Just like total energy or linear momentum, angular momentum is a conserved quantity. Angular momentum consists of a magnitude and a direction. That is, when a body is rotated, the body resists any change in its direction of rotation or plane of rotation and also its rotational velocity. Therefore, angular momentum is conserved for every rotating body. This property of a rotating body is efficiently used in designing a flywheel. A flywheel is designed such that due to the property of conservation of angular momentum, it can efficiently store the rotational kinetic energy, which is given by half I omega square. We have learned about rotational kinetic energy in our previous video. In rotational kinetic energy is equal to half I omega square, where I is the moment of inertia of the body and omega is the angular velocity. Angular momentum is conserved implies angular velocity omega is also conserved, and I, that is a moment of inertia of a body, is constant about an axis. Therefore, a body can efficiently store the kinetic energy which is stored in it. Therefore, flywheel is a device which is used to efficiently store the kinetic energy, the rotational kinetic energy. A flywheel can be a disc or a ring rotated about an axis passing through its center of mass and perpendicular to its plane. The image given here shows the flywheel which we usually use in our laboratories. This is a flywheel. A flywheel consists of a disc. See here we have a disc or a ring, and this is rotated about an axis. This axis which is passing through its center of mass, and it is passing through the perpendicular to the plane of the wheel, plane of the disc. And this is a basic arrangement of a flywheel. So when we rotate a flywheel, it will show moment of inertia. We have learned that the moment of inertia is the resistance offered by a body to start a rotation or to stop a rotation. When a flywheel is rotated and we exert a force to stop, it resists that motion and it will tend to continue in this this rotating motion. It will tend to continue for a longer period. That is, for example, when we switch off our fan, the fan leaves will rotate for a few more minutes because of moment of inertia. That is, it tends to continue in its state of rotation. Similarly, the flywheel, when it is rotated, it tends to continue in its state of rotation. And here I, which gives the moment of inertia, is equal to how much it rotates. So we can actually define moment of inertia as a rotation which is contained in a body. That is, the body resists to stop, or body tend to continue in its state of rotation, and this is called its moment of inertia. So how much the body rotates after stopping actually gives the moment of inertia of that body. So we can also define moment of inertia as the rotation which is contained in that body. So here we are actually using the data, or actually using the principle that the body continue to rotate even if we have stopped the force of rotation. That is, any body which is rotating will exhibit the rotational moment of rotational inertia, that is moment of inertia, and it will tend to continue in its state of rotation. This property is efficiently used in flywheel. So this is the experimental arrangement of doing a flywheel experiment. So here we have a disc. This disc will have a certain mass, and it is rotated about an axis passing through its center of mass and perpendicular to the plane of the disc. So this disc is rotated about this particular axis. To rotate this disc, we use a mass. This mass is first put over here near to the ground, and we will rotate this entire axle such that this mass will go up, winding over the axle. Once this mass is released, once we release this mass will fall under the gravitational energy, because when kept at a height h, it will have a gravitational potential energy. So due to gravitation, when we release the mass will fall down. When the mass will fall down, it will unwind all these windings, and this will tend to rotate this flywheel to a good velocity. Therefore, on unwinding, this mass will come down, and this flywheel will rotate and rotate about this axis. So once it reaches the ground, the mass will detach from the axle. But the flywheel cannot stop rotating because of its moment of inertia. The flywheel will continue rotating even if the mass has fallen down, and this actually gives us the moment of inertia of the flywheel. So to find the moment of inertia of the flywheel, we have to actually measure how much the flywheel is rotating after the mass has actually fallen down. That is, moment of inertia is the rotation contained in that body. So let us look into the theory, how to find the moment of inertia. We have seen that we are using a mass, and this mass is brought to a height h. So here we have a flywheel, and this is rotated about an axis. So here we have a mass m, which is brought from a height, say 0, take it as ground, to a height h. It is brought to a height h. Therefore, the potential energy stored in this mass will be equal to the potential energy stored, gravitational potential energy will be equal to mg into h, mgh. So this is wound over here. This is the potential energy of the entire system right now. So when we release this mass, this winding will start unwind, and this body will start rotating. This mass will start coming towards the ground. This mass will start coming towards the ground, and this body will start rotating. So the potential energy which is stored right now is actually dissipated as the kinetic energy. This is the potential energy stored. So this potential energy which of the entire system is actually dissipated as the kinetic energy of the mass which is falling down. We know that the mass is falling down when it is released. The mass will start to fall down. So when it starts to fall down, it will fall with a velocity v, and it will definitely have a kinetic energy. So this is the kinetic energy of the small mass which is falling down. Again, this potential energy is used again to rotate this body. So the potential energy stored here is used to fall the body, that is used up in the kinetic energy of the falling mass. It is also used in the rotational kinetic energy of the flywheel, and also as friction. This F is friction. And the potential energy stored is used up as kinetic energy, the linear kinetic energy of the mass which is falling, the rotational kinetic energy of the flywheel, and also as the frictional loss. Now the friction is increases with the number of rotation. We know that the flywheel will be attached to some kind of a ball bearing system in these two ends. So it rotates about that ball bearing system. So it will have some kind of a rotational friction, some kind of a friction which is exhibited here or at the windings or somewhere here. So this friction actually increases with the number of turns. That is, when I rotate the flywheel once, it will have some friction. When I rotate the flywheel twice, then it will have 2 times the frictional loss. When I rotate the flywheel thrice, it will have 3 times the frictional loss. Therefore, the frictional loss, the friction energy which is lost will be equal to the frictional force into number of times the mass is actually wound before it was let to go. Therefore, N1 is the number of times the mass was bound before the first windings. It was the number of times the mass was bound before using it. See, in this picture we can see that there are a number of windings, and this windings has actually brought this mass from this point. So all these windings, I can count it as 1, 2, 3, 4, 5, 6, 7, etc. So here we have N1 is equal to 7. So we have 7 windings over here. In each of the winding, each of the time this flywheel is rotating, there is a frictional loss. Therefore, this is our friction energy which is lost due to friction. So energy, potential energy which is actually stored here is used up as the kinetic energy of the mass falling, as the rotational kinetic energy of the flywheel, and also in friction. Therefore, we can equate these three as mgh is equal to half mv square plus half I omega square plus Fn1. Now, we know that when the mass has fallen down, after the mass has fallen down, after the m fallen down, the flywheel will continue to rotate. That is, the flywheel will still have a rotational kinetic energy that is equal to half I omega square. The flywheel won't stop at the moment the mass falls down because it has an moment of inertia. It will tend to continue rotating. Therefore, it will still have a kinetic energy which is equal to half I omega square. And after some time, this flywheel come to rest. And that is, this energy is dissipated somehow. That's why it came to rest after some time. So we can see that this energy is actually dissipated due to friction. And we again know that frictional force increases with the number of windings. Therefore, I can say that the rotational kinetic energy after the mass has fallen down is equal to N2, where N2 is the number of times the flywheel has rotated after the mass has fallen down. Here, N1 is the number of times the flywheel was rotated to bring the mass to a height h, where N2 is the number of times the flywheel has rotated by itself after the mass has fallen down, and F is the frictional force. Therefore, I can equate these because the kinetic energy of the body is dissipated as the frictional energy. Therefore, I can write half I omega square is equal to N2F. From this, I can write an equation for F, that is, F is equal to half into I omega square divided by N2. So I wish to substitute all these together and find an equation for this. That is, let me derive this for a while. So what I have here is mgh. So mgh is equal to half m into. Again, we know that the linear velocity v is equal to r into the rotational velocity omega. So v square will be equal to r square into omega square. So instead of v square, here I am substituting r square omega square plus half I omega square plus, instead of frictional force, what can I write? I can write half I omega square by N2 into, I have an N1 here. So hope it's clear for you. That is half. So mgh is equal to half m r square omega square plus half I omega square plus half I omega square by N2 into N1. So we all have 2's here and we also have common omegas here, right? So why can't we multiply the whole equation, the LHS as well as the RHS? Why can't we rotate this whole equation, the LHS and RHS, multiply it by 2 by omega, 2 by omega square. So I wish to multiply with 2 by omega square in both these sides. So I can get rid of these 2 omega square and 2 omega square over here. So what I will get is 2 mgh by omega square here will be equal to m r square plus I plus I n1 by n2. So I wish to get rid of this n term also. So let me rearrange it as such that mr square is equal to, I have a common I here, plus I have a common I here, so I take I as common, and what I have is 1 plus n1 by n2. Again, I can write this as mr square plus I into, on taking the LCM, I can multiply it with n2. So on taking the LCM, what I get is n2 plus n1 divided by n2. Okay, and this is equal to 2 mgh by omega squared. Again, I wish to divide. I wish to dividing with m in LHS and RHS. What I will get is 2gh by omega square will be equal to r square plus I into n2 plus n1 divided by mn2. Hope this step is clear. I divided the entire term. I divided this with m and m passed down, and this with m, and I could cut m. Here I didn't had a m, so I divided with m. I just taken into this, the same term was taken into this denominator, so I can write it as mn2. Now try to write an equation for I. So we will try to write an equation for I. So let's bring this r square to this area. So what I have here is, I'm just inverting my equation. I into n2 plus n1 divided by mn2 is equal to, so I have this equation. I want to bring this r to the other side. So I have is 2gh divided by omega square minus r square. So to get I, what can I do? Just divide this, just bring this equation here. Just bring this term n2 plus n1 divided by mn2 to the other side. So when I bring it to the other side, the numerator will become the denominator and the denominator will become the numerator. These terms will switch. That is, I can write I is equal to n2m. As I've written here, I can write I is equal to n2m divided by n1 plus n2. This is what the term which I have revised when I brought it to the other side, and the term 2gh divided by omega square minus r square. So I can find the moment of inertia of a flywheel using this equation. Here n2 is the number of times the flywheel has rotated after the mass m has fallen down. n1 is the number of times the flywheel has rotated by us to bring the mass to a height h. Omega here is the angular velocity, and r here is the radius of the axle. So in experiment, what we are actually doing is, the flywheel has a peg, something called a peg, which is attached to its axle. We have a flywheel. A flywheel is something which has a good amount of mass. So it's a three-dimensional body. It's something like a disc. So we have a flywheel, and this flywheel is rotated about this axis. Okay, so what we do is, we will attach a mass m to a string, and the string is wound over this axle, and we will bring this mass to a height h by winding this over the axle, and this string is actually connected to something called a peg in the axle. So it is connected to a peg and this is rotated. So when this flywheel is rotated, with every winding the mass will come up, and the number of windings will actually tells us how much the mass has come up. So N1 is the number of windings which we have done, and after this we will measure the height. We will count N1, we will measure the height. We already know the mass we have subtended. So after this has done, we will release this mass. So this mass will come down along with rotating this flywheel in the opposite direction. So when all this has fallen down, that is when the mass has entirely fallen down, that is when from the axle, when the mass come down and it falls down, but the flywheel cannot, it will detach from the peg. The entire mass will detach from the peg and it fall to the ground. So, but this flywheel will continue rotating. Now N2 is the number of times the flywheel has rotated after the mass has fallen down. Okay, N1 is the number of times when we have rotated the flywheel to bring the mass to a height h, while N2 is the number of times the flywheel has rotated after the mass has fallen down because of moment of inertia. Now from this equation, what all we can find? We can find N2. N2 is the number of times the flywheel has rotated. So we will count that N2 with a reference point. We will have a reference point as a pointer or a chalk mark, which we actually do. So we will count N2. We already have mass M. We have N1 because we have rotated, and we will count how much times we have rotated to bring the mass to a height N. So we have N1. We have the value for G, which is 9.8. We will measure the height h before the mass is released, and R square. R here is the radius of the axle, and this radius of the axle is actually measured using a vernier caliper. Hope you remember in our axle, this is the axle. So axle is not something one dimensional, it has some kind of a thickness. So we will measure this radius of axle using a vernier caliper. Using a vernier caliper, what we get will be its diameter. So we'll divide it with 2 and we will get the radius of the axle, and the last term omega is the velocity, is the rotational velocity of that body. Let us find the angular velocity. So what we can find is actually the average value of angular velocity. That is, when the body, when the mass just slipped off, the flywheel had an angular velocity which is equal to omega, and it gradually came to a stop and it had an angular velocity 0. That is at the time t1. T1 is the time at which the mass has just slipped off. It had an angular velocity omega because it was rotating at that time. But after a time it came to a stop. That is at t2, its angular velocity was 0. Therefore, how can we find the average angular velocity? The angular velocity average will be equal to half of angular velocity plus 0, right? It will be the average of these two values. So it will be half of omega plus 0. Now what we know that the average angular velocity is the number of times it's rotated divided by it's the time taken for the rotation. So, velocity is actually displacement by time. So here it have 2 pi into the number of times it has rotated after the mass has fallen down. So what is that? It is n2. n2 is the number of times the mass has rotated after it, the number of times the flywheel has rotated after the mass has fallen down, divided by the time taken for that. So this time is the time interval between t1 and t2. Right? This is the time interval between t1 and t2. So omega average is actually 2 pi n2 by time. So it is the velocity with which the body was rotating. So it is number of times the body has rotated divided by the time taken for that rotation. So we have our average velocity is equal to 2 pi n2 by t, and we can write it as omega by 2. Therefore, what will be the value of omega? Omega will be equal to 4 pi n2 by t. So what we also have to measure? We also have to measure the time. We also have to measure the time for which the body, the wheel came to a stop. The time from the mass which is released, time from when the mass was just fallen down to the time when the body has released. So we also need a stopwatch to do this experiment. So may I repeat the experiment once again. What we will do is we will have a mass m and we will rotate this flywheel to n1 times such that the mass will come to a height h, and we will note the value for n1 and h. After that we will release the mass. So the mass will come down along with rotating this flywheel in the opposite direction. When it is completely unwound, the mass will fall down. So when at the moment the mass fall down, we will put on our stopwatch and we'll see at what time, how much time it will take for the flywheel to come to a stop. Again we will note how much rotations the flywheel has made before coming to a stop and mark it as n2. Therefore, and also we will measure R using a vernier caliper. So what we all have to measure is a mass, n1, n2, R, omega and time using a stopwatch. Using these measurements and using this equation, we can actually find the moment of inertia of the flywheel about an axis passing through its center and perpendicular to the plane of the disk. Now, let us look into what are the applications of flywheel. Flywheel have immense application in engineering and in our day-to-day life. Flywheel, as we already said, it is used to store the rotational energy. That is, it shows a property that it won't stop at the moment we exert a stopping force. So it will continue to rotate to a certain amount of time. So this property, that it will continue rotating even if we do not give it a force, and this property is used in wind turbines. So that the flywheel will keep the turbine running even if there is no wind force to run the turbine for a certain amount of time. Again, it is used in the motor-driven generators to store the energy. It is used in automobile engines. In the vehicle engines, we also use the flywheels in our cars. In any of the simple automobile engines, we use flywheel so that it will keep the engine running until the engine get the next stroke or the next energy to proceed. So we use the flywheel actually to keep the system running even if there occur a breakage of the energy supply. In automobile systems, we know that the energy supply is not continuous. We supply energy in different times, in different strokes. We supply energy in different strokes. So we do not want our vehicle to stop at every point the energy supply cut off. We want our vehicle to have a smooth running. So we use flywheels as that. The flywheel will store the rotational energy and it will keep the system running until the next energy input comes in. It is also used in locomotive propulsion systems. It is used in technology transit buses. It is used in satellite to control directions. This is also an application for gyroscope. A gyroscope is a device, is a mechanical device which is used to maintain the direction of rotation. The direction, the orientation of any body, we use a gyroscope. So this flywheel can also used as a gyroscope and it is mainly used in satellites so that the direction or the orientation of the satellite is always kept the same. So dear student, so far we have learned about the dynamics of rigid bodies. By this lecture we come to the end of the chapter Dynamics of Rigid Bodies. In this video we have learned about the flywheel, its theory, experiment and its applications. So far in this lesson, this entire lesson, we have learned about moment of inertia, theorems of moment of inertia of different rigid bodies such as a sphere, a cylinder, a disc, an annular disc, a ring, etc. And we have learned about the kinetic energy of a rotating body and also the kinetic energy of rolling bodies. And by the end, we have learned about an application of moment of inertia, and that is flywheel. Hope you have a good learning experience. See you in the next lesson. Thank you.